In the previous presentations, we've talked about where substituents will be depending on where groups are already on the ring. And so if we have the electrophilic aromatic substitution happening, if I have some sort of substituent that is an electron donating group already on the ring, that electron donating group is going to have a preference for the ortho and the para position. The meta position is going to be the minor, not that it's not going to happen, but it's going to be a minor of the products. And so the other things to keep in mind in terms of these reactions is that if your electron donating group has a lot of steric hindrance, the para position is going to be preferred, and that's because the ortho and the ortho position will be more blocked than the para position. And so another thing to keep in mind is that if the electron donating group is not very bulky, there are two ortho positions, and so in theory, as long as the ortho and para positions are not blocked in any way, they should. The two ortho positions are equally likely, but there's only one para positions, so you should have almost 2 times as much ortho than para, as long as the electron donating group is fairly small. When your molecule contains an electron withdrawing group, on the other hand, the ortho and the para positions are not preferred. And so that would leave us mostly with the meta positions. So the ortho and the para positions tend to be the minor product. The major product will be the meta. Now, I'm going to emphasize this here. This does not mean that you get a lot of meta. The electron withdrawing group is going to make the reaction quite slow because it's a deactivator, and so your yield is going to be low. And the only way for you to facilitate this reaction to not give you low yields is you can't use the same reaction procedures as you would for the electron donating group. And typically that would mean that the reaction time would have to be extended quite significantly. So instead of, let's say, a reaction that usually takes 10 minutes, you may have to leave these reactions for 30 minutes or more to even see the same amount of product. So it will take a little bit more. Our next area of consideration is what if you have multiple substituents on the ring. And so there is a hindering effect that can happen if the groups are directing in a particular location. If you have a substituent that will be added based on the different groups on your ring, and one possibility is between those groups, then it's technically too hindered. They both direct in the same position, and that's because the chloro, even though it's an electron withdrawing group, is our exception, that it does still direct in the ortho and the para position, but it will not very little product will happen and form in the position between the two groups. When the groups are in the same direction, they will produce products kind of in the same direction, like I said, but if they're opposing each other, which is the next point that we'll talk about, then the stronger activator will win out. In the case below, we have something where we have two groups directing in the same position, but we don't have that meta to prevent the two groups from blocking one particular site. So if we have a substituent that is a stronger activator, that stronger activator is going to dominate the position in which things are going to lie. So for instance, OH is a stronger activator, so it will dominate over a methyl group. Another change that can be done is it has a lot to do with the amino group. There are 3 things that the amino group change that we have here can do. So recall that I said when you were trying to do reactions with the amino, they will react with the Lewis acid to form this ammonium type salt, which then deactivates the ring, makes the ring harder to react, but it also takes the Lewis acid out of solution, which would mean that you would have to add excess Lewis acid, quite a bit of excess, just to make the reaction work. But the second problem is the amino is already deactivated, and so you'll get different directing effects on the product. So one thing that we can do is that we can turn the amino into an amide. Amides are actually weaker electron donating groups. They're also quite bulky. So there are several things that they're going to end up doing for us. Because the amino is no longer a base, it cannot react with the Lewis acid anymore. So that is one thing that can happen. The other thing that can happen is the amino group being quite bulky will have a preference for the para position. So if you're looking for something that will give you the ortho, this is not going to be the best way that you can do that, but it will have a preference for giving you your product in the para position. And so to get the amino back is what we did in Unit 1. It's just a hydrolysis turning an amide back into an amino group. The next thing that we have to worry about with the amino groups is that the amino groups are strong electron donating groups. Okay, so before we do that, again, the amide is not a base because they don't have that lone pair able to act as a base. It's somewhat localized, and the bulkiness of the group promotes para. So our other thing is the amino group is a strong electron donating group, and it's one of the strongest electron donating groups that we have. We can add alkyl groups and it can make it even stronger. But one of the problems with it being a strong electron donating group is the fact that you can have poly-EAS reactions, so multiple EAS reactions happening on that molecule. And so you'd have to modify the conditions of the reaction so that it slows down significantly so you don't get too many additions onto the ring. Or we could utilize the same concept that we had there in 1 and 2, make it an amide, because amides are not very strong electron donating groups. And so one of the changes that we can make, so we can make it into an amide, which is a milder electron donating group. And so if we were to look at the amide, we have a lone pair on the amide that is more localized. There's a hydrogen also on that nitrogen that I'm just not drawing in right now for space sake, but it's more localized. And because it's more localized, it's not quite available to activate the ring very much. And so, yes, it can donate into the ring, but not very strongly. So it's a mild electron donating group. But we can easily remove it by hydrolysis. Other changes that we can make are things like turning phenol into alkoxy groups. So, for instance, like anisole, or into esters. By making these groups into esters and still having the lone pair next to the ring. So that's important. If the lone pair is not next to the ring and the structure is drawn for the ester the other way, they're now electron withdrawing groups. But with the oxygen on the ring rather than the carbonyl on the ring, they're still electron donating groups, but they're just milder, very similar to the amide versus the amino. For the OR groups, that can be help us in terms of sterics and promote the para position. We can also interconvert ketones to alkanes, and by converting a ketone to an alkane, you can use something that has an electron withdrawing group, convert it to something that has an electronic donating group, and back and forth. We can also do reactions at the benzylic position and change its behavior. So for instance, if we add an electron halogen or an OH group into the benzylic position, it makes it an electron withdrawing group because now there's a partial charge at that location. If we oxidize the benzylic position, we can also make benzoic acid if it's primary or secondary. And by doing that, now you have an electron withdrawing group. Our last topic for this unit is nucleophilic aromatic substitution. There's going to be a couple of minor things after nucleophilic aromatic substitution. This is the last main big topic. We'll also talk about other addition reactions onto your ring. But first, let's talk about this nucleophilic aromatic substitution. And one thing that we know about nucleophilic aromatic substitution is that we have the only time we ever see this reaction happening is when we have strong electron withdrawing groups on your molecule, and you usually have to have very strong ones, and two, you're going to need to have something on your molecule. You're going to need to have something on your molecule that can act as a leaving group. And as a sub one, it's even better with more electron withdrawing groups. So the more electron withdrawing groups, the better. So typically something that might have this ability would be something of this sort. So you need to have some sort of leaving group, like a halogen or a tosylate, and you need to have strong electron withdrawing groups. Without this, these reactions don't happen. The basic idea is it's almost like a kind of the opposite to electrophilic aromatic substitution. And the way that it happens is slightly different. So you're going to also need, as my fourth category, a strong base for this. So we need a strong base, and what it will do is attack at where the chlorine is, open my pi bond. So we end up having an OH in that position. And then we have a negative charge at the position where the strong electron withdrawing group is. And we'll talk about why that's important in a second. But then the structure, which is called a Mesenheimer complex, these Mesenheimer complexes are not stable, just like rhenium or sigma complexes are not stable because you break aromaticity. By breaking aromaticity, it wants to reform, so the chlorine gets kicked out. So it's also important that your leaving group is better as a leaving group than the nucleophile that you added. So if OH was a better to come off, then the chlorine would not come off. It would be the halogen. So in this case, the chlorine gets kicked off, you reattain aromaticity, and then you get your OH. So in terms of what's going on here, and in terms of why you have to have these electron withdrawing groups, so these electron withdrawing groups essentially is making your aromatic ring more electrophilic, so that your nucleophile can attack. Normally your aromatic ring is a nucleophile, and then it attacks an electrophile. Now, the second thing that we want to talk about is where does the electron withdrawing groups need to be? So that is our next thing to add to this list. So we have 5 things already. There is a 6th one. The electron withdrawing groups need to be in the ortho or para position to the leaving group. And here's why. So in this Mesenheimer complex, so compared to what we just had before, we have a negative charge at this location, and we can have resonance stabilization happening in the ortho and para position. So if our compound has its NO2 or its electron withdrawing groups in the meta position, we're going to see a very different behavior of our Mesenheimer complex. And it's one in which we have no resonance stabilization with the nitro group to help us. So the OH attacks, the double bond forms charge right here. But no matter what we do, our negative will never be at the carbon with the electron withdrawing group. And so we miss an opportunity for an extra stabilization, and that extra stabilization is one of the reasons why we need to have your groups in the ortho and para position. Our last real reaction that we'll talk about, and that you don't need to be able to draw the mechanism for this, but it's very similar to a lot of things that we've seen before, except it's mostly going to be focusing on the fact that we have to use these harsh conditions to do these substitution reactions, and that's why we typically don't see them. It is a possibility, so on paper you can do it. On a test, I'm not typically going to ever ask you for these, but your textbook does have some of these options. So if I took, for instance, hydroxide to do a substitution, you learned in Organic 1 that this does not happen. And in fact, this reaction doesn't work as a SN2 reaction, but there is a similar type of reaction that can happen where the OH attacks and kicks out the leaving group. But the only way that this mechanism can happen is at very harsh conditions, very high temperature, sometimes very high pressures. And so this addition elimination reaction, we can use a variety of different nucleophiles to do these. They have to be strong nucleophiles, and they have to be very, very high temperatures. So typically nothing lower than 350 degrees. It's usually very harsh, which oftentimes can damage your molecule. So in theory, we can do this, but in practice, it's not done as often. So in class, we'll focus a little bit more on the EAS reaction, but this is one that you should have an idea about.